regiochemistry then. I think last time we were looking at directing groups. For example, a toluene that's too far out of the page. Okay. And we remember we were going to put some nitric acid, sulfuric acid, we're going to nitrate this thing, right? And we looked at some of the potential positions that this could occupy. We looked at ortho positions, meta position, and para position. Though actually I don't think we looked at meta yet. We had looked at ortho and para. Oh, thank you. This is what happens when I get flustered, huh? Okay, hold up. Where does connect? Sorry. Okay. Well, hopefully this stuff should still be on your last page of notes. I'll stop for a sec so you guys can catch up. Thanks, Eric, for letting me know. So, starting with toluene, doing an electrophilic aromatic substitution on the ortho position gives you the nitro in the ortho position. We can also get it in the meta position or the para position, right? So we can get presumably a mixture of 3 products. And we saw that in this case, the winner was this one by a little bit, followed by the para position, and then the meta had very little, right? And so generally para is preferred to ortho, but since methyl is pretty small, there's not a lot of steric problems with a methyl group directing your substitution. So this one happens to be ortho, but generally speaking, para is the preferred position for making your second substitution on a benzene if you've got an activating group like this. So, go ahead.
Why is it preferred?
We'll see. So, the reason right now it's why is para preferred, we'll see with it's both sterics and electronics. Ortho is preferred electronically but not sterically, because that methyl group is presumably blocking things, but it's a small group, so it's not as strong as something like, say, a T-butyl group. And then just remember also that ortho, there are 2 ortho positions, right? Just like there are 2 meta positions, but there's only 1 para. So if we look at a distribution, we saw, I think, if I remember correctly, we had about 63, like 2%, and what is the rest going to be? 35% then? So that's the ratio we got, but remember that the ortho is kind of counted twice because there's 2 ortho positions, right? We could have put the nitro group on that side, right? It's symmetrically identical, so that's why this one is going to be higher in this case. So with methyl groups, it's harder to say if you're going to get ortho or para, but we're going to see that just don't use methyl as a directing group, and you'll pretty much always get para as your dominant position for attack. So if we look at the if we just take a look at the sigma complexes for all of these, that's the intermediate step, right? Where we have the carbocation still floating around in there. If we take a look at those, I guess we're going to not have that. So this is for the ortho position, right? We will have attacked ortho to our methyl group. By doing so, we will consume that double bond, and we're going to end up with the carbocation there next to the methyl. Notice that this is a tertiary allylic carbocation. It's a good thing, right? It's very stable. If we resonate this thing around, we'll see that, yes, we can make other positions have it, but that tertiary allylic is the best. We can put it here if we want to. I'm not going to put CH3. And then if we go ahead and resonate again, why not? we can end up moving it to the other position. But again, we see here that the best position was the one that I guess we had already had, which was the tertiary allylic, right? Because these are all secondary allylic positions, which are less stable than the tertiary one. If we do para, we see that we're going to get the same thing. If we just take a look at the para sub, so if we use the double bond at the bottom to attack the nitronium rather, and then we'll end up with a carbocation there, which can resonate as always. So we can move this down. If we do that, we end up with our carbocation tertiary allylic again, so that's a good thing. And if we really want to show the other one, yeah, we can resonate that as well, but we're going to end up back with secondary allylic. So between these, again, that middle one is going to be the preferred one. And if we just finally look at meta, if we look at meta, the meta position here, if we resonate this, we see that no matter how we resonate this, we are still going to end up having our carbocation on secondary allylic only for all three of these. So, and then these. So, all of these secondary allylic, but with the meta or ortho and para, we can get tertiary allylic positions for our kind of sigma complex. That's going to stabilize it, right? Tertiary allylic is more stable than secondary. So that's the reason that ortho, para, and preferred when we have what's called an activating group on. So I'm going to just turn it sideways so you can see here. So we have two scenarios in which we have tertiary allylic sigma complexes, where we have that carbocation adjacent to the methyl group, so it's got some electron donating from the methyl group, and then we have others as well. Meta, we don't have this benefit, so meta is going to be left behind. So as a result, we're going to see that the methyl group will direct, it's going to direct it to ortho and para positions as a result. I guess I need to be grammatically correct there. So it'll direct it to the ortho-para position as a result because of the resonance. So methyl group will direct this. If we take a look at another substituent, instead of a methyl, why don't we do something a little bit more electron donating? Let's look at phenol. If we nitrate this, we're almost exclusively going to get ortho and para. Okay, and I'm just going to copy this because why not? We're almost exclusively going to get ortho and para here, and we'll see why that's going to be. We pretty much will not get the meta substituent. So we can actually look at this right away without actually even doing the reaction. We can look at phenol itself. So what's different between the phenol and the toluene that we did in the last example here, toluene can't really, I mean, the benzene can just resonate among itself, but the toluene doesn't really participate in the resonance. It's there to stabilize the carbocation. However, if we have something like an oxygen on there, we can actually use that to resonate into the ring. Notice that we can say, aha, we can resonate onto that ortho position, or, oh god, this is going to be ugly, but we can resonate onto the para position as well, and symmetrically the other side we can resonate onto the ortho. If we follow the blue arrows, we end up getting a negative charge on our carbon. The other two double bonds stay the same. And if we follow the green arrows, I'll move up a little bit so we can see that. So if we follow the green arrows, we end up with same thing, but now we have our lone pair on the pair position. And so now we can see this is a very good place to attack our electrophile, right? We have now negative charges that can be localized onto specific carbons. Notice the ortho and para carbons are the ones that would get that negative charge. The meta position will not. No matter how you resonate, you'll never get this onto a meta position. So these now become stronger nucleophiles. So much so that if you remember, we couldn't put just bromine with our benzene, right? And just putting bromine with benzene didn't do anything. We needed a Lewis acid to make that work, right? We had to put iron or aluminum in to brominate this. But it turns out that as a result, we're going to see that if you have something like this, you do not even need the Lewis acid. You're just going to brominate the heck out of this. You're going to brominate every ortho and para position. It's like crazy because it's so much more reactive. It's much more activated towards electrophilic aromatic substitution. We now have negative charges on our benzene ring. Those can attack electrophiles much more easily than just the double bond could, right? That's a site of instability, right, in the resonance form, and so that's something that can be used to react. And so we see here that because these are much stronger, we see that no Lewis acid is necessary. For this particular reaction. And so you can see you can go crazy with these things. So we're going to see that a lot of these substituents can activate a ring towards electrophilic aromatic substitution. And those are all going to be electron donating groups. So let's take a second here to identify some. We're going to see that we're going to have strong activators of rings. So these substituents strongly activate benzene, meaning they make it more reactive towards electrophilic aromatic substitution. And these are going to be things with lone pairs that are adjacent to the ring. For example, phenol, aniline, a phenoxide, any substituted aniline. All of these are going to be good activators of our benzene. We're going to see that because they have those lone pairs adjacent to the ring, they can donate that electron density in, and we're going to end up having strong activation. R can be H for these as well, for the amine there. Generally speaking, your amine is the strongest. I mean, well, technically this one's probably the strongest because it's negatively charged already. But going on, it's probably somewhere around this order of things. So I'm not going to really worry about you making distinctions between the strong activators themselves. But in some scenario where you run into something like this, generally you're looking at things that can accommodate that positive charge better. So obviously number one there, the phenoxide, when it resonates in, the oxygen is neutral. You just put a carbon ion somewhere, which is going to go ahead and react. With the amine, nitrogen is better at holding a positive charge than oxygen is, right? Because nitrogen is less electronegative. So nitrogen is going to be better than oxygen is, similarly speaking. And then if you have more stuff on, that can make it better or worse, just depending on what you have. So number 4 is kind of a wild card. All right, so these strongly activate your rings. We're going to see that we also have moderate activators. And these are going to be, they have lone pairs adjacent, but they're delocalized. And what I mean by that is we might have something like an ester, but it's the non-carbonyl side of the ester. So we do have lone pairs here that could feed into the ring, but they can also resonate the other way. So they're not as strong as activators. We're going to see amides behave the same way. Amides would also be moderate activators. And then another one is ethoxy groups. So ethers are also moderate activators. You might consider them to be, you might think they might be strong because they do have lone pairs adjacent that aren't, that are not delocalized, but evidence shows that these are actually only moderate activators, these ethers. So we're going to see here that those will be our moderate ones. All right, and then our weak activators are going to be our alkyl groups, because these ones, they can contribute by stabilizing the carbocations in the sigma complex, but they can't resonate. So, I mean, methyl, ethyl, whatever. Any sort of alkyl group will be weakly activating. So they're weak activators. So you can have as many alkyl groups as you want. Those are going to be weak activators. So they still activate your ring. They make it more reactive, but not nearly to the level of the moderate activators, and even better than the moderate activators are the strong activators. So strong activators have lone pairs adjacent that are not delocalized away. Moderate activators have lone pairs that are able to resonate away, and the methoxys, or ethers. And then we also have the alkyl groups as weak activators. So all of these things help make your benzene more reactive towards things.
That's just a question.
Mm-hmm.
Activator just means it could make the benzene more reactive.
Correct, yeah. So it's going to help you make that reaction faster or more thermodynamically favorable. So Okay, so yeah, so activators make your benzene more reactive. I'll write that down. They make your benzene more reactive to electrophilic aromatic substitution. And we're going to see it'll be the opposite for deactivators, which we'll see next. So electrophilic aromatic substitution, EAS. That's what that is. Okay. So we're going to see what those deactivators are. Notice all of these are electron donating groups. That's the pattern here. We're going to see that deactivators are going to be withdrawing groups. And it's interesting because let's take a look at what's going to happen if we have an electron withdrawing group on a position here. So let's say we've got, go ahead.
Sorry, what did EAS stand for?
Electrophilic aromatic substitution. I shall write it. Electrophilic aromatic substitution.
Oh, thank you.
We're going to see we will have also nucleophilic, which will be NAS. But electrophilic ones are where most of the stuff is happening. So, alrighty. So, if we go ahead and attempt to nitrate this, we get almost exclusively, interestingly enough, the meta product. So, I'm not going to even draw them, but you would know what they look like, right? Just putting them in different positions. So if we nitrate this, we're going to see that we get the meta position reacted. And again, we're going to take a look at the sigma complex of what these look like once we have reacted them. So, boo, boo, boo. I guess let's go ahead and do an ortho one first. If we try and resonate this thing around, we have a lot of resonance for this one. Just like before, we'll have 9 total resonance forms. Oh joy. And we're going to see the important part will be this last resonance form here. And I'm going to actually draw out our nitro group, because there is something important about the nitro group that's going to make this not so great. Notice here we have a positive charge next to a positive charge. Not a good thing, right? This is very sad. Sad resonance. This makes it incredibly unstable to resonate this way. So we saw that with some of the activating groups, we actually had stabilized our resonance, or we had actually made a negative charge somewhere that we can just attack with and keep things neutral, or have our positive charge on an oxygen or something without having an incomplete octet anywhere. This is the opposite case. So when we have an electron withdrawing group, if we put something on the ortho position, we can end up with a resonance form that has 2 positives next to each other. So where all the resonance helped us in the activating side of things, here it actually, the resonance hurts us a little bit. So the first 2, yeah, those are good resonance, right? Moving the carbocation around, always a good thing. But the third one there, you end up putting it next to another positive charge. So sad things happen, and it's unfavorable. So you're not going to end up getting that carbocation. We're going to see we're going to end up with better ones. If we take a look at the, let's do the meta, I guess. we've got our positive charge there. If we resonate this one around, boop, boop. We're going to see, no matter how we resonate this, we are going to end up having all of these in relatively good resonance positions. We do not have any, we're not going to end up with that positive charge next to any of our nitro groups. Remember that nitro group has a positively charged nitrogen, so none of these have that sort of sad resonance that I mentioned. So all of these have carbocations there that are all secondary allylic. We have no conflicting charges here. So we're going to end up seeing that the meta position is ideal when we have an electron withdrawing group like this on. If we take a look at the para position, we're going to see we have the same story as with the first one. So if we resonate, oh my god, I'm drawing so many resonance structures. My hand is going to be hurting at the end of this. Okay, so we have moved our carbocation up, and note when we do this again, if we resonate again, we are going to end up making our very sad carbon that has the positive charge next to the nitro group. Do we all see how this is happening? So, sad things, not good. So, not good. So, as a result, we're going to see that these electron withdrawing groups are actually going to direct things to the meta position instead. We're going to see that in general, electron withdrawing groups will direct to the meta position. So because of that, and as a result, you'll pretty much only ever get meta if you're starting with something that's got an electron withdrawing group and nothing else. So electron withdrawing groups direct to the meta position, and they also will deactivate the ring. So notice that with all of these reactions, we had benzene acting as a nucleophile, right? It's attacking an electrophile. So if we put an electron withdrawing group on a benzene, that electron withdrawing group will take in electron density to itself, thereby making benzene a less effective nucleophile. We're taking it away. We're taking electron density away from it. If we just resonate, if we just look at resonance forms of the nitro group, or we could do it with a different one, we're going to see that we can end up just taking, if we just resonate things, we end up removing electron density from our ring. We end up making our ring positively charged. If we just resonate like this, if we do this resonance, what do we end up with? We end up with a carbocation. Remember when we resonated the oxygen in the phenol, we ended up with a negative charge in our benzene? That's donating electron density to the ring, making it a better nucleophile. This is the opposite. resonance here makes the ring less nucleophilic. In fact, the ring right now is an electrophile. We're going to see that we can actually have something attack the ring when we have a deactivating group on it. So previously, I'm going to scroll up. We saw, if we resonate with this oxygen, we end up with negative charges on the ortho and para positions. That's a very good nucleophile. If we resonate with the nitro group, we end up with positive charges at the ortho and para positions. I guess I didn't draw the para one, but you could end up with a para if you didn't do that first blue arrow. If you just started here, if you followed the green arrows instead, you would end up getting the positive charge on the para position. We're going to see later that it makes it more susceptible to nucleophilic attack at those positions. But in terms of electrophilic aromatic substitution, EAS, the reactions we've been studying, where benzene is the nucleophile, these reactions, or these substituents, deactivate your ring. They make it less reactive. So, in general, we're going to see that we also have strong deactivators. So strong deactivators are going to be much like the ones we've seen before. We have the nitro group. We have, some positively charged nitrogen. So nitro has a positively charged nitrogen, right? Something that's a quaternary nitrogen or a protonated nitrogen. So R can be H or an alkyl group for any of these. So even just ammonium or anilinium, rather it would be called, would be a strong deactivator. Because again, when you look at these things being attacked, or rather attacking something, you end up with a carbocation next to the positively charged nitrogen. That's not a good thing. We also see that if we have something that is heavily halogenated, that would be a strong deactivator as well. So if you have one of these three things, that's a strong deactivator. And if we want to think about weak or moderate deactivators, those are going to be things with carbonyls. So all of the things with carbonyls next to them. So we can have aldehydes, ketones, carboxylic acids, amides rather. What else can we have? I mean, technically halogens as well. Any of these things can be an R group on this it's essentially anything with a carbonyl. And it's got the carbonyl side towards the benzene. We saw that esters, I should put that, esters that had the non-carbonyl oxygen towards the ring are moderate activators. But if we have the opposite case where we have the carbonyl side close to the benzene, they're moderate deactivators. So they're going to withdraw electron density instead of donate it in. And then another one would be our sulfonyl or a nitrile. Those would all be moderate deactivators. So any of those ketone things, carbonyl things I should say, or some of these other groups are moderate deactivators. So these are all electron withdrawing substituents. And So as a result, they will make your ring less reactive. Important to note that all strong or moderate deactivators they direct it to the meta position. Now you've probably noticed that I didn't say all deactivators do this. All strong and moderate ones do. But we haven't mentioned weak deactivators yet, have we? And we're going to see that weak deactivators actually direct to orthopara. And so we saw this because you end up either putting resonating away your electron density, or you end up with a positive charge adjacent to something that is fully positively charged, or in this case, partially positively charged, right? We end up, if we were to resonate or do our sigma complex, this carbon here is positively charged partially, right? And so if we end up with a full positive next to a partial positive, that's still not a good thing. So that's why these are only moderate. Same with the nitrile, we have a slightly positive things there. So as a result, all those are partially positive, all these are fully positive, or this one is so partially positive that it counts as a full positive. So, because having 3 halogens on there, they're all going to be withdrawing electron density, so that carbon is extra positive. I'm going to put a little minus there, just so. Okay, anyways. Let's talk about the weak deactivators. What about those? These are going to be our halogens. Our halogens directly on the ring. We know that halogens are electron withdrawing, right? These are electronegative. They're going to want to withdraw electron density towards themselves, right? So they are electron withdrawing groups, so they do deactivate your ring. So let me put that out first. So halogens are electron withdrawing groups. They will deactivate the benzene. Make it less reactive. But they can also resonate electron density in. They also stabilize positive charges, right? Because they are electronegative, they're happy to be next to a positive charge, right? They're already partially negative, so if you put a positive next to them, that's great. They can also resonate in. So if we look at the sigma complex for, say, we're nitrating our chlorobenzene, what am I doing here? Okay. So if we go ahead and put it on the ortho position, if we resonate stuff around, I'm just going to show the one resonance here. I think you guys are pretty sick of me drawing resonance structures, but we'll do it. We know that this chlorine is electron rich. And it could decide, okay, well, carbon with your incomplete octet, I might help you out a little bit. and resonate in and help you, because remember, incomplete octets are worse than having a positive chlorine. Positive chlorine still has its octet. This will help make that that carbocation go away, right? It becomes now a chloride or chlorine ion, I suppose. And so that's better, right? Because incomplete octet on carbon versus positive charge on chlorine, positive charge on chlorine is better, right? Incomplete octets are inherently much more unstable than any other sort of positive charge. So because of that, because this is electron rich, it can resonate in a little bit and help out to stabilize that positive charge. And so we're going to see that when things go to the ortho or para positions, we end up stabilizing our sigma complex with a halogen. Even though they are technically electron withdrawing, they have the ability to resonate in that the other things do not. None of our other deactivating groups can resonate into the ring. They can only resonate away from the ring. All right, so all of these resonate away from the ring. Our halogens can resonate into the ring. And so as a result, in green we'll say that halogens are weak deactivators. Fine, I'll write it out. They are ortho-para directors. So they still direct substituents to the ortho and para positions, but they do make your benzene less reactive. So if you want to end up nitring this, you're probably going to have to heat it up a bit or something. You have to give it some extra energy to compensate for that. Okay. So, with that all in mind, it may be helpful to make a little chart. We're going to see that we have our strong activators, our moderate activators, our weak activators, and our weak deactivators are all going to be ortho-para directors. Our meta-directors are going to be our strong deactivators and our moderate deactivators. So I'm going to write out all those letters. So our ortho-para directors are all of our activating things as well as the weak deactivators. Our meta-directors are going to be our strong and moderate deactivators. And yeah,
Sorry to ask this question, but what does it mean by directing it?
it means it forces it to go to a certain position. Or, I mean, it doesn't force it, but when you do these reactions, if you have an ortho-para director, your substituent will end up predominantly on an ortho or para position. If you have a meta director on there, you're going to get your substituent on a meta position.
Okay.
Does that make sense? Okay. So yeah, it just remember that whatever we have on our ring, that substituent will direct things either to the ortho-para positions or the meta positions. So whatever that R group happens to be, it will essentially, I don't want to say force, because it implies that there's some sort of like, whatever, fine. It forces substituents, whatever you're reacting it, to go to those other positions. So it's not a stupid question, by the way. That's totally legit. So okay, so whatever your substituent is, if you're going to be reacting it, you're going to end up guiding your new substituent to one of these positions based on whichever category your R group fits into. So let's take a look at a few last little rules here, and then we'll start planning things out. I've got 3 more rules for you. And we'll do them in, I don't know, how about dark blue? If you have multiple R groups on your benzene, multiple things on it, your strongest activator will win. If you are putting a new substituent on. So if, for example, you have two groups on a position and you attempt to, let's say, we can even just put, let's not do Cl2. Let's do why don't we do let's do a Friedel-Crafts on this. Both the hydroxy group and the methyl group are ortho-para directors, right? Para position is blocked, so they're going to direct ortho. So we have to determine, is it going to go ortho to the hydroxy or ortho to the methyl groups? And we always will go with the stronger activator. Hydroxy is a strong activator, methyl is a weak activator, so hydroxy will win. And so as a result, we will put this adjacent to our, this is kind of a bad example. Let's make this an OR because that OH could be nucleophilic, and it'll do other things, but we'll just say it's an OR instead. OR is still a stronger group than methyl. So as a result, we're going to end up putting our new substituent on in ortho to our stronger activator. So because we had a competing thing, they're both activators, but they activate different positions. The methyl group would activate these 2 positions. The oxygen there will activate those 2 positions. Right? The para position is not available because they are already occupied. So we are going to direct it, and so we're going to see here that the stronger activator, which is the oxygen, will direct the new substituent to the ortho position to itself. So not to the methyl group. All right, so that's kind of our first rule. I lied, there are 4 rules. Isn't that fun? So if if 2 relationship, let's try that again, relationship the new sub will not go between them. What I mean by that is something like this. This methyl group will direct our new sub to one of these 3 positions, right? Ortho or para. Our oxygen would say, okay, we're going to direct you to one of these positions. We will never put, here, I'm going to even block off the para position here. I'm going to block this one off. Let's say we have, I don't know, BR, whatever, who cares? BR is a deactivator, we're not even going to compare it. We're going to say, okay, well, where are we going to put this? Well, our oxygen is the strongest activator here, so it's going to direct it. And we might say, oh, well, we can direct it to this kind of middle position, right, in between the methyl and the oxygen, and that'll make everybody happy. But that position will not get attacked because of steric reasons. So there are some still sterics to consider with all these electronic rules that we're talking about. So if we go ahead and nitrate this or whatever, we will end up getting our nitro group up there. We're not going to get a mix of products. We're going to end up putting it ortho to the oxygen, but also not adjacent to the methyl. So that's other ortho position does not get attacked because of steric reasons. All right, methyl is a kind of terrible choice here. We'll make it T-butyl. We'll make it really obvious. Boom, T-butyl group. T-butyl group will shield that other position. So all of these things are going to be important because we're going to be synthesizing. That's always a fun word in this class, right? We're going to be synthesizing a whole bunch of polysubstituted benzenes. And so we have to not only consider where things are being directed electronically, but we also have to consider sterics in these things. So we're not going to see that we're going to nitrate that other position. It's just not going to happen. So that other position is not a viable place for the nitro to grow. So this is too blocked. Like, right, the sterics are blocking that position. So we're not going to be able to get that one to go. All right, and then two kind of special more rules. Your Friedel-Crafts reactions will not work if the only is a strong deactivator or moderate deactivator. The Friedel-Crafts reactions will not proceed if all you have is, say, a nitro group or a sulfonyl group. You have to have at least a weak deactivator or better to get Friedel-Crafts to work. So it's not going to work if you have, say, acetophenone. If you have acetophenone and try to, say, put another acetyl group on, it's not going to work. You need to have some electron density in your ring to get a Friedel-Crafts to happen. So you have to have, at minimum, a halogen on there or something more activating. A methyl group, methoxy, an ester with the oxygen side. So something better needs to be there for Friedel-Crafts to work. And then the last one is can't nitrate aniline. So aniline, if you try to do this, you're going to get some sludge. You will not end up getting your nitro group on the para position or whatever. It's just not going to work. Because the nitric acid is going to oxidize the amine there, and we're going to end up with all sorts of weird, crazy stuff that's just going to become this gross sludge. So these are kind of special things. So you can't Friedel-Crafts unless you have a weak deactivator or better. You can't nitrate aniline. anything in the presence of aniline, even if there's, say, a methyl group, a couple of methyl groups or whatever. It's just not going to work. So any sort of aniline you can't do a nitro reaction in the presence of aniline. All right. So those are all of our rules. Question is, do I want to start talking about synthesis now, or do I want to introduce nucleophilic aromatic substitution and just do all the synthesis on Wednesday? I think we'll be better prepared on Wednesday. Yeah, we'll do that. So, I want you to make charts of all of these reactions or something, condense all this information down. So about how your directors are guiding new substituents. You know what? Let's do a few examples, and then we'll see from there. Okay. I have a couple prepared here. Which one do I want to do? All right, let's say I want, no. Let's say I want, all right, let's go ahead and make something like this. All right, let's make this. COOH carboxylic acid, right? Here, I'll even draw it out. So, how the heck are we going to do this? Well, first thing to think about would be what reagents and stuff do we need to even put these groups on? Right? If we know we can put this thing on by putting nitric acid and sulfuric acid, right? How do we put a carboxylic acid on? It's not one reaction.
Is it the Friedel-Crafts?
So Friedel-Crafts would be the first step. Friedel-Crafts will give you either a ketone or an alkyl group, right? I like that. I think alkylation is a better way to go here, sure. What else? But how do we go from an alkyl group to a carboxylic acid? Something we looked at last chapter, perhaps? Something on your last exam, perhaps, as well?
I was going to say, ozonolysis.
You've got the right idea. What type of reaction is ozonolysis? Oxidative cleavage, right. Do we know any other way to oxidatively cleave anything next to benzene?
Probably is, but I'm just blanking.
Probably is, huh? Maybe, do we remember on our exam we had this dude with mystery reagent turned into... Actually, no. We had this as mystery. Oh, well. Remember this sort of thing? And we also got our oxalic acid out. How did we do this? What was the reagent there? Oops, that should be no H.
Do we use E and KMNO?
Yeah, right. So remember that any alkyl group can be cleaved off in aromatic using KMNO4 and heat to produce a carboxylic acid. Absolutely right. So that would be the first step, right? So we know that these things can be put on with phenol crafts and then oxidative cleavage. So not necessarily ozonolysis because that works for alkenes or alkynes, but easier is to just cleave it using just cleave an alkyl group directly. So with this, we know now how to put these two subs on. 3 subs, rather. 2 of them are the same, though. But now we have to consider what order to put them on. Right? So all of these things are deactivating groups, right? Carboxylic acids are moderate deactivators, and nitro group is a strong deactivator. We want to look at the positions relative to each other, and that will probably help us out in determining what to put on first. But we also know that we have 2 steps to do with Friedel crafts. Friedel crafts will give you an alkyl group on there. And alkyl groups, remember, are orthopara directors. So it could stand to reason. Actually, you could do either way with this one. You can see that you can. There's multiple ways to make this, and a lot of these syntheses, by the way, there are many ways that you can make them. But generally speaking, it's better if you have a more active ring to do stuff with. So it probably makes sense if we notice these relationships to each other, like the carboxylic acids are para to each other. The nitro group is ortho to one acid, but meta to the other. If we put the nitro first, that would mean that we need to put everything else meta to it. So we can put one carboxylic acid meta, but how do we get that ortho one? Kind of hard to do that, right? But if we put the carboxylic acids on first as alkyl groups, we would probably get para substitution of alkyl groups. And after that, we can then nitrate, because alkyl groups are ortho directors, right? We can say, aha, it's going to go ortho to one of these alkyl groups. Or we can say, actually, let's go ahead and oxidize these and then go ahead and put the nitro group on, because now they're meta directors, but it's still meta to one of them, so it's okay. We got some nice symmetry here. So, but the first step in either case is to do the nitration last, because otherwise we're not going to get them to the positions they need to be. So we probably want to do the other part first. So if we do a Friedel crafts on this, it's generally better to do acylation, generally speaking, because acylation, remember, will avoid polyalkylating your thing. Friedel crafts alkylation, you get alkyl groups everywhere. So generally speaking, it's better to do acylation and then Clemenson reduce it down. So if we do a Friedel crafts on this, what do we want to put? What sort of alkyl group do we want on this thing? Doesn't really matter, but go ahead. What's your favorite?
I know what it looks like. I just forgot.
Describe it. What does it look like?
It's like C.
Very good. We are studying carbon. Very good.
So it could be just like any.
We're going to cleave it off, remember? Any alkyl group treating with KMNO4 will cleave it into the carboxylic acid. So choose your favorite. They're all your favorite. Fine. Let's put an isopropyl on. If we do this, I'm sorry, this would be we'll do the acylation. So here, what do you want? Propyl, why not? Actually, that's butyl. Why not butyl? Sounds good. Let's do this once. If we do this, we end up with this guy on it. What type of director is this substituent? The AlCl3 is part of the other bit.
So deactivate.
That's a deactivator, right? It's a moderate deactivator. So this is a meta director. We can't use a meta director because we need the other para position to be done. So we probably will need to do something with this. How can we make this into a para director? Clemenson. I agree. What is the other one? HCl? I think so. Zinc mercury HCl gets rid of the carbonyl. 1, 2, 3, 4. We now have a para director, right? I would say probably not ortho because look at how bulky that thing is. It's probably going to knock anything away. So more likely than not, we're going to get the para position. So if we need to put an alkyl group on that, do the same thing. We can say, okay, now we're going to do this again. And why not? We'll just do the Clemenson all at once. One, two, three, four. Oops, too many carbons. 1, 2, 3, 4. So now we have our squid-looking thing. That's great. Now, if we go ahead and nitrate this, it'll go to really any of those positions. And it doesn't really matter what, because symmetrically, no matter where that nitro grows, it's going to be equivalent in position. It'll be ortho to one of them, meta to the other. So, does not matter what. So we can go ahead and nitrate this. And I'm going to say that because these positions are all equivalent, I'm just going to put it in the same spot that our thing was before, the one that we have in the product. These are just getting uglier and uglier. 1, 2, 3, 4. And last step, KMNO4, and heat it up, and poof, we will end up with our product. We could have done these in the opposite order. We could have cleaved this and then nitrated, but that's a little bit harder to do. Now these are both meta directors, but thankfully that nitro that we need to put on is still meta to one of them. And it doesn't really matter where that nitro goes because again, symmetrically it's equivalent. So technically this would work, but it's harder to do because we have 2 moderate deactivators on our ring. It's going to take a lot of energy to get this reaction to happen. But if we keep our moderate or our weak activators on until the very last step, that's going to help our reaction to go forward. So generally the black pathway here is a little bit better, right? If you wanted, you could probably try as well doing a Friedel-Crafts alkylation with an isopropyl chloride, but you do run the risk of polyalkylating all over the place. However, though, because isopropyl is fairly bulky, you might just get the para to each other. that probably would work, but a little bit riskier, because you could end up potentially alkylating various other positions as well. So Friedel-Crafts, remember, Friedel-Crafts alkylations are not controlled reactions. As soon as you put it on, it becomes more reactive, so it's going to go ahead and grab another one. And then it becomes more reactive, it's going to go ahead and grab another one. And you can end up just going crazy. These acylations, though, remember, once you put it on, it's deactivated. So it's less likely to react again until you get rid of it using Clemenson. Now you have an activating group. Now you can throw on more stuff and go from there. So generally speaking, pattern-wise, you do want to keep your activating substituents on as long as possible, because those will just help your reactions go forward. Does that make sense, that we want to hold on to our activators, whatever those are, for as long as possible?
So we don't typically want to use alkylation.
Correct. Alkylation is great if you want T-butyls, but that's pretty much it. Because T-butyl will only ever go, it'll stop after the para one, because it's now so bulky you can't reach those ortho positions anymore. But if you just throw in, say, like, if you go like this, you're going to end up with some benzene, you're going to end up with some monoalkylated, you're going to end up with some polyalkylated, you're going to end up with some trialkylated, tetraalkylated, who knows? Because each time you add on an alkyl group, you're making it more reactive. And the more reactive you make it, the more likely it is to go ahead and attack the next one. So you're going to end up with this whole mess of products. So it's a hard reaction to control, and so I would generally not recommend it for synthesis problems, unless you're putting on a T-butyl group. If you're putting on a T-butyl group, you will probably stop at 2. You're going to end up getting this, and that's it. Not a problem. Because the T-butyl group is so bulky that those other positions just will not be able to attack. And so you'll stop there. So if you want a di-T-butyl substituted benzene, go right ahead. But otherwise, I would say do acylation and then reduce it. That's going to be a much more controlled process. Because again here, as soon as you put on your first alkyl group, it's more reactive. Now it attacks again. As soon as you put on an acyl group, though, you make it less reactive, thereby reducing the chance that you're going to get 2 acyl groups on there. And even if you were to get a second acyl group, it would go to a meta position. So, not ideal. Alright, so that's the hint. So, Friedel-Crafts alkylation is not so great. Alright, let's do another one. Okay. How about we do this one? Any questions, by the way, on the last one, or on the idea of the alkylation? Actually, let's make this an H2. So, lots of ways to approach this. I can think of like 4 different ways right now. But good thing would be to do is to... Oh, we haven't learned how to put oxygens on yet, have we? Because we haven't talked about nucleophilic ones. Okay, here, we'll cheat. Boom. How are we going to go from phenol to this thing?
Do we use the one with the ALCl3 and the... I forgot what the name was for it. The
There's
one
a
with the
couple
chlorine.
ones with ALCl3. The Friedel crafts,
I think that's what it was called.
the one we just did.
Yeah.
So
The one where it's chlorine and double
yeah. So Cl2, right? Yeah. That would be how we can put the chlorine on for sure. So that's a good step. Let's start with figuring out what reagents we need to put on this thing. Honestly, we probably don't need the AlCl3 because the OH group is so strong that we probably would just get the chlorination and be done with it. Probably not necessary, but doesn't hurt, I suppose.
Can we use like iron or like any loose acid?
Yeah, you can use yeah, iron would work there, I would say.
Yes.
Typically aluminum is just cheaper, so or easier to use because the iron one gets all sludgy and aluminum chloride is a nice powder, so it's just easier to use. So I think that's why we typically say that. But yeah, FeCl3 would work as well. But even here, because you have such a strong activator, you don't need a Lewis acid to begin with. So, but we'll put those there. How do we change this into an ethyl O-ethyl? Williamson, yes. So that would be a base, say OH minus, and some sort of halogenated ethyl group, right? Let's not use OH minus because OH minus would be could be a nucleophile, so let's use sodium hydride instead, or T-butoxide, whatever, some sort of non-nucleophilic base would work there. All right, now how do we put an NH2 on? How do we get this thing there?
First, we're going to add NO2, and then we're going to reduce it to NH2.
Beautiful. What's the reagents to get it to reduce?
We could use zinc.
Yep, zinc will work. And then you then you need a base at the end. So great. So we have all of our ways of making these. So that's step one. Figure out what the heck you need to work with these. Next thing we want to do is note that since we're starting with an OH, OH is a orthopara director, right? Para generally is preferred, so we probably would want to nitrate this first, right? We could do the Williamson first, doesn't really hurt anything. But either one will work. So we can say that the first step would be nitrating. Doesn't really matter again. We're going to keep our strongest activator, might as well. So if we do our HNO3, H2SO4, we end up nitrating. We probably don't want to put this into the amine quite yet, because if we make it in the amine, if we put it as NH2 instead, that's a stronger activator than OH, which means that our chlorine would then go ortho to the amine, which is not where we want it. We want it ortho to the OH, or ortho to the ethoxy. So I would probably not do the second half of this quite yet, because we don't want it to mess up our regiochemistry. So while we still have the OH as our strongest activator, we can go ahead and put some chlorine in there. Again, Lewis acid optional, because we have a strong activator on there. We probably don't need the chlorine, or the AlCl3 or FeCl3. Oh, that's ugly. Let's try that one again. And, I mean, the rest doesn't matter. To the rest of them. Probably because we're just reducing things or changing things that are now already on our ring. For the next ones, it doesn't really matter. So whatever you do next, we've got the reduction here and our Williamson. Those two bits can go in whichever way you like, and then we can end up with our product. So since we're out of time, so we'll end up getting our oops, that's an NH2 at the bottom. So it's just a matter of thinking. You have to think, where do you need things to go? How do you get them there? And therefore, once you know kind of those two things, you can deduce what order is best to do it. And again, here we have options. Like we could have done the Williamson first. It doesn't matter. Like that doesn't really change things. It makes it a little less strong, but it's still a moderate activator, so it's still okay. It's still pretty good. So, yes. All right, so that's what we're going to be working on. So next time we're going to start with nucleophilic aromatic substitution and then elimination addition. Sorry, elimination addition, and then we're going to do more synthesis. So you'll probably do more synthesis in lab as well. So that's probably what you'll do tomorrow. So okay. Alrighty then. See you guys on Wednesday. Take care.
Thank you.
Mm-hmm.